waiting for my first slide to move forward, but thank you for staying for the last presentation. Oh, there we go. It was too many slides at a time. For the very last presentation of the afternoon. And it may be a bit of a strange jump from RISC to quantum computing. And I'll make the jump for you now, and I'll just simply say, those of you who just left, they engage in a big risky behavior because they miss out on an important intellectual topic, and they will regret because in 3 years there will be sessions of a whole day on quantum computing. And then those of you who stayed, you can say, I paid attention already in 23 when this was just in the beginning. So thanks for the introduction. Yes, I'm director of ADIA Lab, which is a new research lab. It started exactly a year ago here in Abu Dhabi, created by ADIA. And we are here in ADGM, moved into ADGM in August, and engaged in computational and data research and basic research in application of computational and data science. So what I would like to talk about is quantum computing, and there are a few messages, since I only have 10 minutes that I would like you to take away with, and I gave you the 4 messages right up there. First of all, quantum computing is using principles of quantum physics. It is a very different type of computing than what we're all used to from the traditional digital computing. And then I say maybe a few things about some of the things that are different on quantum computers, like the qubits that you may have heard about. Then just, and this is the main point here, is the promise of quantum computing is huge. And it may take, however, still many years of research to realize this promise of quantum computing. And as a bonus, I give you one important trivia piece of knowledge. What you see on the right side, that's the picture you usually see when people talk about quantum computers, but I disappoint you. This is not a quantum computer. This is a big and expensive refrigerator. It's a refrigerator made out of gold, which is produced by this company in Finland, Bluefors, which any single quantum computing company that is building is superconducting qubits kind of quantum computer needs it to chill the chips down to almost 0 degrees. And so it's beautiful, it looks great, and it's wonderful, and has this mystique, but it's not a computer, it's a refrigerator. So you can impress your friends when they say, I've seen a quantum computer, just have, now you didn't see a quantum computer, just a refrigerator. The actual superconducting chips just look like regular, almost like regular computer chips. So why is quantum computing so exciting? It has a promise in a number of different application areas. It has a very big speed up over classical computing in certain applications. It may be an important tool for quantum simulation. This is important to keep in mind. Richard Feynman, who is often credited with having promoted quantum computing, said basically, nature is quantum, so we should use quantum computers to simulate nature. And this is actually probably the most promising physical application, is to simulate quantum systems in chemistry and materials with quantum computers. There is a big opportunity to use quantum computers to solve optimization problems. This is maybe the biggest industrial application. And then there are cybersecurity applications. In the positive way is that in the quantum world, you can have unbreakable protocols, but you can also use quantum computers to break existing quantum security protocols, like, for example, the RSA protocol based on factoring of large integers. So quantum computers are built out of qubits, quantum bits. And what are qubits? Very simple. This is maybe overly simplistic. It is overly simplistic, but is that you think of a bit in a computer as a 2-state device that's either on or off. So think of it like a light switch that you can turn and off. And then in computer science, you learn how to use that simple device to do all the calculations. A quantum computer has a state which is a combination between on and off. So you can think of it, but this is not exactly the right way of thinking it, as a dial that you can dial between 0 and 1, between on and off. But to be a bit more mathematical, and that's the only mathematical slide that I'm using this afternoon, is that actually for quantum computer, the qubit is storing a combination of 0 and 1. And the combination is with two complex numbers, a and b. And this is such that the a squared plus b squared, that is the norm of these two common numbers, is 1. And that means that you can think of it not as a linear dial, but as a number that is on this so-called Bloch sphere. And this is expressed in sines and cosines. So what does it all mean? It means that you can actually build a quantum computer with these qubits, but the qubits are not the real quantum essence. There are other things that are happening. Entanglement is the one which makes the quantum computer really work. This is the quantum. The rest is just basic linear algebra. The power of a quantum computer is coming because of the power of the qubits. And you've probably heard that there are quantum computers today that have up to 100 qubits. And a quantum computer with 100 qubits can encode up to 2 to the 100 different states, for example. And this means the storage capability of such a computer is astronomical, truly, because 2 to the 100 is almost the number of particles in the universe. So this is where the big computational power of the quantum computers are coming. Now, where are we today? Today, quantum computers have been proposed in the 70s, and some first big proposals were made in the 80s. And since the early 2000s, companies have been started building quantum computers. D-Wave was the first one, and I remember it was probably 2005 that I had the honor of being in their product announcement. And now you have many of the big names in computing, like Google and Microsoft and Intel and IBM, are all engaged in quantum computing projects. But what's important is, what this slide here really shows is that there are many different physics technologies that are used to build the qubits. And so this is basically a reflection that a quantum computer is still at the stage of a physics experiment. And so it's not yet, yes, you can get access to quantum computers, but I'd say this is still very early. And if you go back in the history of digital computing, we are in the equivalent of the 1950s. So if you put in 1947, the first transistor being built at Bell Labs, and in the 1950s being the first computers being built. And so first business computers were built in the early 60s. So we're still, if you like a computational history back to back, quantum computers are still in a very early experimental age. Now, that being said, of course, the potential excitement is huge. And there has been significant investment, both from the big companies and in many small startups. They're all listed here. You can look at the North American companies and the European companies here, and the investments they have received. Some of them have significant, several hundreds of millions of dollars of investment received. And also the big players like Google, IBM, and Amazon and Intel have invested significant amount in their in-house development. So there's a lot of money going into quantum computing, and that has created a lot of additional excitement. On top of that, there's a rumor that China has invested of the order of 10 billion also in quantum computing, which is of course always raising the stakes in North America and in Europe. Now, a market research firm, and since we're in a finance week, I want to show this also, is estimating, this is from Hyperion, which is used to be a subsidiary of IDC, is estimating that by 2025, the quantum computing market will be about $1.2 billion US. Now, if you are computer scientists, that may be a big number, but if you keep in mind that the total IT industry is a $4 trillion industry, so that barely makes a dent. It's not just a little scratch. So what's the big hype about? Well, the big hype about is that this is potentially the application field. And so the interesting thing is that everybody has been asked, where will quantum computers find their first application? And for some reasons that I explain a little later is that financial is seen as one area where quantum computers might find first application have the biggest impact. And that's coming ahead of quantum research and cybersecurity and then chemistry. So there is significant impact that quantum computing can have on our lives. And the future is, or the potential impact that quantum computers have is that they can provide solutions, potential solutions to problems that have many different possible solutions. So for example, logistics problems in transportation. And a good example of this is falling under combinatorial optimization problems. There's the expectation that quantum computing will accelerate machine learning further. And you've heard one of the panelists earlier this afternoon being very enthusiastic or concerned about the potential of combining quantum computing with AI and machine learning. And then there is this possibility that I pointed out is that quantum computers can accelerate chemical simulations. And the reason why I think there's excitement is, and this is, I've been signaled to end, is that we're just at the bottom of an S-curve. We're here where there's ferment, and as you know, technology follows these S-curves. We're before the ChatGPT of quantum computing has arrived. It may arrive in the next 2 or 3 years. So stay tuned for exciting developments, and I should be finishing here. So I'll end up with my advertisement. If I hopefully got you interested and excited about, come back here to this wonderful location, ADGM. In this very auditorium in January, we'll have a conference on quantum computing for finance, organized jointly with ADGM and Imperial College London and Nanyang University of Technology in Singapore. So if you enjoyed ADGM Finance, Abu Dhabi Finance Week, please come back in January and learn more about quantum computing for finance. Thank you.